Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The mid-20th century found the nascent field of nuclear physics in a state of profound intellectual schism. Following the immense theoretical and practical upheavals of the preceding decades, the subatomic world of the nucleus presented a landscape rich with experimental data yet fractured by competing theoretical paradigms. Two great pillars of thought stood in apparent opposition, each offering powerful explanations for a distinct subset of nuclear phenomena, while remaining mute on others. On one side stood the nuclear shell model, a triumph of quantum individualism championed by Maria Goeppert-Mayer and J. Hans D. Jensen, which envisioned nucleons, protons and neutrons as independent particles orbiting within a mean potential well, their stability governed by the same quantum rules and shell closures that dictate atomic structure. This model exquisitely explained the exceptional stability of nuclei with so-called magic numbers of nucleons, a clear echo of the noble gases in chemistry. On the other side was the liquid drop model, an idea with roots in the work of George Gamow and brought to fruition by Niels, Bohr and John Wheeler, which treated the nucleus as a classical, incompressible fluid. This collective view successfully described the overall trends in nuclear binding energies and provided a compelling, visceral mechanism for the dramatic process of nuclear fission. Yet, one could account for the quantum discreteness of magic numbers, while the other could explain the collective cleavage of the nucleus. The field was thus divided, possessing two successful theories that described the same object in fundamentally incompatible terms. It was into this fertile, albeit conflicted, intellectual environment that the work of Aage, Niels, Bohr, Ben Roy Mottelson, and James Rainwater emerged, culminating in their definitive 1957 review, Collective and Individual-Particle Aspects of Nuclear Structure. This work was a grand synthesis, a conceptual bridge thrown across the chasm separating the particle and elective, demonstrating that these two views were two sides of the same, more complex, nuclear. The impasse preceding this synthesis was defined by the successes and stubborn failures of the incumbent models. The shell model, with its elegant inclusion of a strong spin-orbit coupling term in the nuclear potential, provided a theoretical foundation for the empirically observed magic numbers of 2, 8, 20, 28, 50, 82, and 126. Nuclei possessing these counts of either protons or neutrons exhibited markedly higher binding energies and greater abundance, a phenomenon the liquid drop model could address in a superficial way. The shell model gave a precise reason these numbers corresponded to the complete filling of quantized energy shells, creating a stable, tightly bound configuration. It successfully predicted the ground state spins and parities of a vast range of nuclei, a testament to its power in capturing the quantum mechanical behavior of individual nucleons. Its deep limitation, however, arose when observing nuclei far from these magic configurations. Experimental measurements, particularly those advanced by Charles Townes and his contemporaries using microwave spectroscopy, revealed that many of these nuclei possessed very large electric quadrupole moments. A quadrupole moment is a measure of a charge distribution's deviation from spherical symmetry. A value of 0 implies a perfect sphere. The observed values were enormous, orders of magnitude larger than what a single odd nucleon orbiting a spherical core, as pictured by the simple shell model, could possibly generate. The implication was unavoidable: these nuclei were behaving as if they were substantially deformed, shaped like ellipsoids or footballs. The liquid drop model, conversely, had no conceptual difficulty with deformation. As a charged fluid droplet, the nucleus could be set into vibration or rotation, naturally assuming non-spherical shapes. This picture was instrumental in explaining nuclear fission, where the nucleus, upon absorbing a neutron, could oscillate so violently that it elongated and ultimately split into two smaller droplets, releasing a tremendous amount of energy. The semi-empirical mass formula, a cornerstone of the liquid drop model, provided an excellent fit for the binding energies of nuclei across the entire periodic table by treating the nucleus as a bulk material with volume, surface tension, and electrostatic repulsion terms. Its deficiencies, however, were as profound as its successes. The model was fundamentally classical and continuous, lacking any mechanism to explain the quantum shell effects that produced magic numbers. It offered little insight into the detailed spectra of lowlying excited states, or the specific magnetic moments and transition probabilities that characterized individual nuclei. The very existence of nuclear isomers, long-lived excited states, was a mystery from a purely collective viewpoint. The field was thus armed with a model for the individual and a model for the collective, each profoundly incomplete, waiting a conceptual breakthrough to unify them. The genesis of that breakthrough began with a beautifully simple insight from James Rainwater at Columbia University in 1950. He considered the perspective of the shell model and asked a crucial question: what effect would the motion of the outer, or valence, nucleons have on the nuclear core they orbit, according to the shell model. These nucleons move in well-defined orbits. Rainwater reasoned that the centrifugal pressure exerted by these orbiting particles would distort the supposedly inert core. The liquid drop, a nucleus with nucleons in elongated orbits would naturally push the core into a prolate, or cigar-like, shape, while nucleons in equatorial orbits would flatten it into an oblate, or discus-like, form. The core, once conceived as a rigid stage for the individual nucleon's performance, was now reimagined as a dynamic, responsive medium. This insight was the key. It suggested that the individual-particle motion and the collective properties of the nucleus were coupled, one influenced the other. The nucleus was a composite system, where the state of the individual particles determined the collective shape, and that collective shape, in turn, defined the potential in which the individual particles. It fell to Aage, Bohr, and Ben Mottelson at the Institute for Theoretical Physics in Copenhagen, the institute founded by Aage's illustrious father, to take Rainwater's idea and develop it into a comprehensive, mathematically rigorous framework. Over the next several years, they constructed what became known as the collective model, or the unified model. Their approach was to formulate a new nuclear Hamiltonian that explicitly incorporated this coupling. This total Hamiltonian could be conceptually separated into three components. The first term described the collective energy of the core, treating its deviations from sphericity as a set of dynamical variables for small deformations. These could be described as surface vibrations, quantized into phonons. For stable, large deformations, the dominant collective motion was rotation, with the core behaving like a quantum mechanical spinning top. The second component of the Hamiltonian was the familiar shell model term, describing the independent motion of the valence nucleons in a spherically symmetric average potential. The third component, the crux of the entire theory, was the interaction term. This coupling term connected the coordinates of the individual nucleons to the collective variables describing the shape and orientation of the core. It quantified precisely how the potential experienced by a nucleon depended on its position relative to the deformed surface of the nucleus. The predictive power of this unified framework was immediate and spectacular. It directly resolved the long-standing puzzle of the large electric quadrupole moments. In the collective model, a deformed nucleus possessed an intrinsic quadrupole moment related to its stable, non-spherical shape. The quantity measured in the laboratory, the spectroscopic quadrupole moment, is a projection of this intrinsic moment onto the axis of quantization, and the theory provided a direct formula relating the two. The model's predictions matched the enormous experimental values with remarkable accuracy. Perhaps even more compelling was its explanation of the energy spectra of deformed nuclei. For nuclei with a stable ellipsoidal shape, the model predicted that the collective rotation of the entire nucleus would give rise to a characteristic pattern of excited states known as a rotational band. The energies of the states within this band, the theory showed, should be proportional to the expression J times the quantity J plus 1, where J represents the total angular momentum of the state. This precise rotational energy signature had been observed in the spectra of many heavy nuclei in the rare-earth and actinide regions, a beautiful regularity that had completely defied explanation within the pure shell model. Bohr and Mottelson's theory predicted these bands with stunning fidelity, establishing a new and powerful form of nuclear spectroscopy. It further accounted for the probabilities of electromagnetic transitions between these states, providing a detailed and verifiable picture of the nuclear dynamics. The 1907 paper in Reviews of Modern Physics served as the capstone of this theoretical edifice. It was far more than a research article. It was a manifesto for a new understanding of the nucleus, synthesizing years of theoretical work and experimental evidence into a single, coherent narrative. Its publication solidified the collective model as the dominant paradigm for describing low-energy nuclear structure, and its influence rippled through the field. The model's framework proved to be incredibly fertile ground for further development. One of the most significant extensions was the work of the Swedish physicists Sven Gerst and Nielsen. Building directly on the Bohr-Mottelson approach, Nielsen calculated the single particle energy levels for a nucleon moving in a realistic, axially deformed harmonic oscillator potential. The result in Nielsen diagrams became an indispensable tool for nuclear physicists, allowing them to predict the spins, parities, and other properties of deformed nuclei by simply filling the calculated energy levels with nucleons, in direct analogy to the way one uses molecular orbital diagrams in chemistry. Further refinements incorporated the concept of pairing interactions, a residual short-range force between nucleons analogous to the electron pairing in the theory of superconductivity. This addition, leading to the superfluid model, was crucial for correctly describing the moments of inertia of rotating nuclei and the energy gap observed in the spectra of even-even nuclei. Decades later, the conceptual legacy of the collective model continued to shape the field. The interacting Boson model, developed in the 1970s by Quito Arima and Francesco Iacello, approached the problem from a different mathematical perspective, using the algebraic techniques of group theory to describe nuclear excitations in terms of interacting bosons. This more abstract model, however, was shown to be, in certain limits, a mathematical realization of the collective vibrations and rotations first described in physical terms by Bohr and Mott. The reception of the unified model was overwhelmingly positive, as it solved so many consistent puzzles with such elegance and power. The intellectual synthesis it represented was so complete that it effectively ended the foundational debate between the Individual-Particl and collective viewpoints. The 1975 Nobel Prize in Physics, awarded jointly to Bohr, Mottelson, and Rainwater for the discovery of the connection between collective motion and particle motion in atomic nuclei and the development of the theory of the structure of the atomic nucleus based on this connection, was the formal, if somewhat delayed, affirmation of the revolution they had engineered. The work represented a profound maturation of nuclear physics, moving it beyond simple, idealized models toward a more nuanced and realistic description of a monumentally complex quantum man-body system. It revealed the nucleus as an entity where emergent, collective phenomena arise directly from the underlying interactions of its constituent particles. In conclusion, the 1957 work of Bohr, Mottelson, and Rainwater stands as a landmark of 20th century physics, a testament to the power of synthesis in scientific inquiry. It confronted a field divided by two seemingly irreconcilable theories and demonstrated that the truth lay in their union. By recognizing that the nucleus could be simultaneously a collection of individual quantum particles and a collectively deforming fluid, they resolved a central paradox of their time. Their unified model provided not merely a qualitative picture but a rigorous, quantitative framework that explained a vast swath of experimental data, from static quadrupole moments to the dynamic spectra of rotating nuclei. Its legacy is a profound shift in our perception of nuclear matter, revealing it as a rich microcosm of man-body physics where the interplay between the individual and the whole generates a stunning complexity of structure and behavior. The theory's enduring influence, seen in the tools and concepts that remain central to nuclear science today, underscores its status as one of the great unifying achievements in our long quest to understand the fundamental architecture of the natural world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.